Alright, hello everyone, this is John, and today I want to show you how to manually calculate a one sample t-test, literally just how to calculate a one sample t-test by hand. So this is going to be a three-part series. In the first video I'll show you just a step-by-step process on how to calculate a one sample t-test, doing it manually by hand with a provided example. And then the next two videos will just follow suit to this first one. The second video will then show how to calculate confidence intervals, effect size, and percentage of variance for a one sample t-test, which will also be by hand. And then the third video will just be an example of how to do a one sample t-test using RStudio. So whatever example that I'm providing throughout this, the final video will just replicate that example using RStudio, so you can see what the hand calculations look like and then how the calculations look like in RStudio and how they compare, which means they should be the same. So let's begin. So when you're calculating a one sample t-test, there's a few steps you're most likely going to want to follow, whether you're calculating this test from raw data or if you're calculating this test from a textbook or a question you're answering in a textbook. Usually the first thing you're going to want to do is state your null and alternative hypothesis. The null hypothesis is most likely going to be H0, and it's most likely going to suggest that the sample mean, whatever the mean is for the t-test you're going to calculate, is going to be no different than the population mean, which is usually the mean for the population you're comparing your sample mean to. So most likely your null hypothesis is going to state H0, your mean, the sample mean, is going to equal the population mean, suggesting there's no difference between the two means. The alternative hypothesis, on the other hand, is just going to suggest H1, that the mean for your sample population, the mean for your sample is going to not be equal to the mean of the population. It's good to state this quite clearly, just so when you have the results you can state whether the null hypothesis can or cannot be rejected. Usually a very good step to begin with. The second step that you're going to want to follow is to determine whether you are using a one-tailed or two-tailed test. If you're using the best way to explain it is if you're answering questions within a textbook, it's going to state whether to use a one or two-tailed test, and then you'll just follow whatever is being stated in the question. On the other hand, if you are doing this calculation on your own accord, or you're using raw data to calculate the t-test, it's really up to you whether you choose a one or two-tailed test, but most likely it's going to be based on your hypothesis or previous research. If you have no support for your claims on whether the mean should be greater or less than the population mean, you're most likely going to use a two-tailed test, because the two-tailed test suggests it could go either direction. It can be greater than or less than. We're not 100% sure. But if there's previous research to suggest that one-tailed should be used, meaning that it is suspect that the results should increase from the population mean, then you most likely are going to use a one-tailed test. But something to keep in mind, because this is going to help you when interpreting your results in the t-distribution or t-table. Now the third step, which is something that's commonly overlooked, is to determine whether the data is normally distributed. If you're answering questions in a textbook, you probably can skip over this part of when calculating a one sample t-test, as in many cases you're not expected to know whether the data is normally distributed or not. But on the other hand, if you're using raw data and you're going to be doing these calculations, you should have data that reflects a histogram like what is displayed on the left-hand side of the screen here. It should have that pyramid bell-shaped curve. If it looks anything like on the right-hand side of the screen, you probably should not be using a one sample t-test for this type of data. So most likely you should be displaying the raw values in a histogram to see how it fluctuates, or really how it's laid out in a histogram, and if it represents anything like a normal bell curve. Now we're going to start going into the actual calculations of the one sample t-test. As you can see, the first three steps are really just setting up the design, or setting up some of the fundamentals for the test. But step 4 here is when we start calculating things, and here we're going to calculate what is known as the degrees of freedom. The degrees of freedom is going to be based on your sample size. So for example, if you have a sample of 20 individuals, your degrees of freedom is going to be 20 minus 1, which is 19. The degrees of freedom that is being shared here, which is being presented, is the actual formula. df is going to equal n minus 1, where n is your sample size. It doesn't matter how big or how small your sample size is, it's always going to be n minus 1. Now step 5 is to calculate the variance, and the variance can differ based on the question you're provided or if you're using a raw data set. But what it's asking for in this formula, to calculate the variance, which is s squared, you need to have the sum of squares value from your data divided by the sample minus 1, similar to the degrees of freedom. So the sum of squares, if you're doing questions within a textbook, most likely it's going to provide you with the sum of squares value. If it doesn't provide you with the sum of squares value, it might present to you something such as the standard deviation. In either situations, these two values can be worked. They almost reflect one another. So for example, the standard deviation here is just the square root of the variance. So s squared, which is above here, you just square the standard deviation and then you get the s squared. So for example, if you have a standard deviation of 3, you square 3, which would be 3 times 3 equals 9. So your variance in this situation would be 9. But if you're given the sum of squares within a question, it's quite simple. You just plug it into the formula, your sample minus 1, and you get the variance. The second scenario, and if you're working with raw values, this is most likely where you're going to fall in line. You'll actually have to calculate the sum of squares. I'm not going to cover how to calculate the sum of squares within this tutorial, but it is something that you'll be expected to do if you're working with raw values. You're going to have to create a summation score, and you're going to have to divide them in order to get that sum of squares. So step 6 now is to calculate the estimated standard error. Quite simple. If you followed step 5, you've calculated the variance, and the n will be provided to you. That will be the sample size, or how many people you collected. So it's just going to be your variance divided by n square root to get the estimated standard error. Now step 7, which is now approaching the final part of our t-test, is to do just that, is to calculate the actual t-statistic. The t-statistic is, once again, just a plug-and-play formula. You'll have the mean for your sample, which is represented by the larger m, and then you'll have the mean for whatever group you are comparing to, which would be the population mean. You're just going to subtract the two and then divide by the estimated standard error, which you calculated in step 6. Now step 8 is to look at a t-distribution table to determine significance. In this situation, if you're using a textbook, a t-distribution table will be most likely provided at the back of the textbook or within an appendices. Or if you go online, you should be able to find one of these tables on any website if you do a Google search. What you are required to do, though, in order to determine if your t-statistic is significant, you have to use your degrees of freedom. So whatever your sample size was, n minus 1 is your degrees of freedom. You're going to have to use the degrees of freedom plus your t-value and locate them, because there's going to be a region within the table. It's called a critical region. If your t-value is greater than that critical region at whatever your degrees of freedom is, then you can determine whether the result is or is not significant. Usually if it's larger or past the critical region, it's significant. If it's lower or not within the critical region, it's not significant. But once again, this is also going to depend on whether you're using a one-tailed or two-tailed test. The reason it's going to depend on these two functions is because it's just going to depend on how you interpret the table. If it's a one-tailed test, the critical region's a little bit more lenient, meaning the critical region's usually smaller than if it was a two-tailed test. But that is totally up to either the question you're answering or the analysis that you're doing. You should have selected one of these at the beginning. You don't usually select them once you have your results calculated, because you have a hypothesis to support why you would choose one over the other. Now step 9, which is the final step now, is really to state your findings. You should provide a written statement of your results. Were the results significant, yes or no? And really, can you reject the null hypothesis? Was your sample mean equal to the population mean, yes or no? And then you would provide what is called scientific notation, where you would provide the DF value, your degrees of freedom within brackets, which equals the T value, and then the P value, whether or not it was significant. So it would look something like here, that is highlighted in blue. So here is literally the step-by-step process on how I would tackle a one sample t-test manually by hand. Something to keep in mind if you're going to do one of these tests. But let's go into a example question now and actually do the one sample t-test together. So you have an option here. If you want, you can pause the video, read the question, and start doing the test. Or you could just follow along and I'll read the question out loud and do each step by step. All right, I'm going to continue. So the question goes like so. Bill finds out that the average student at his college campus walks approximately 7.05 kilometers a day, which is a population mean of 7.05. So Bill decides to buy a pedometer and measure how much he walks over the next 7 days. Bill finds out he walks approximately 9.0 kilometers a day for a mean of 9.07 with a standard deviation of 2 kilometers. So using Bill's data, calculate a one sample t-test, two-tailed, and determine if Bill walks more steps than the average student at his college campus. So right away, you should see that all the information is provided for you within the question. It's just a matter of using this information to calculate the one sample t-test. So here I'm going to highlight some of the key elements that you'll need in order to answer the question. Number one, we have the population mean of 7.05. The idea here is that college students at this college campus walk approximately 7.05 kilometers a day. That's the population mean. Now, over the next 7 days, which is a sample of 7 technically, Bill decides to see how much he walks, and he walks approximately 9.07. So what you have here, and I have it down in the table below, is an n equals 7. So the idea is Bill is using each day that he walks as one of the cases within his sample. So his n is 7 for 7 days, with a mean of 9.07. So a lot of this has already been calculated for you. It's just a matter of putting in the t-test. And obviously here, the standard deviation, which is something you will also need, as I was mentioning previously, is the questions are either going to provide you with a sum of squares or a standard deviation. If you're using raw values, you're going to have to calculate both. But here, it's quite simple. It's being provided for us. And we can see the standard deviation is 2. So that's important to keep in mind for the calculation. And then the final important thing to mention here is that the question is asking for a two-tailed test. It's asking for two-tailed, suggesting the result could be greater or less than. There's no hypothesis to suggest why it should be a one-tailed test. So it's a two-tailed test. And that's how you're going to interpret the results within a t-distribution table, is using the two-tailed method. So the first step is to state the hypothesis. It's a good step to begin with, at least to wrap your head around the question, and depending on who you're answering the question for or for yourself, you should have hypothesis to share with others. So the hypothesis here would hypothetically be one of the following. The null hypothesis would be that there would be no difference between Bill's walking data and the walking data from the average college student. We can see within the table that the average college student does walk less than Bill. Bill walks 9.07 with a standard deviation of 2, but that doesn't mean that Bill significantly walks more than the average college student. We need to do the one sample t-test to determine if it's statistically significant or not. And that's where our alternative hypothesis comes in, which suggests the mean will not equal the population mean, or Bill's walking data will be different from the average college student who is walking on the campus. So we have our null and alternative hypothesis. Let's see what happens. So the next step is to determine if you're using a one or two-tailed test. This is quite simple. It was provided in the question, but it's something for you to think about if you're using raw values and you need to do all these calculations on your own. The one or two-tailed test should follow your hypothesis more or less. Step 3, is the data normally distributed? This information wasn't provided in the question, and we're going to have to just assume it is normally distributed. So in this situation, we'd actually have to skip this step. Step 4, to calculate the degrees of freedom. Quite simple. The degrees of freedom is 6. All we're doing is n minus 1. It's our sample minus 1. Bill walked for 7 days. So our sample consists of 7 different cases minus 1, which equals 6. I'll put that in the table down below here, and we'll continue. So we have the degrees of freedom. Step 5 now is to calculate the variance. Quite simple. We do not have the sum of squares, but even better, we have the standard deviation. Our standard deviation is 2. So we can actually, and we actually know the standard deviation equals the variance if it is squared. So if we do 2 squared equals 4, and then technically the variance is going to equal 4. Pretty simple. Now step 6 is to calculate the estimated standard error. We've already calculated the variance, and we know our sample is 7, so we can actually use our variance. 4 divided by 7 square root, where you'll get 0.57 square root, which equals 0.75. We can add the estimated standard error to our table. And now step 6 is to calculate the actual t-statistic. Bill's mean for his walking data was 9.07, so we're going to subtract that from the population mean, which is 7.05 of walking data. Then we're going to divide it by the standard estimated error, or the estimated standard error, sorry, which is right here in our table, 0.75. We divide it, and we get an actual t-statistic of 2.69. And with this t-statistic now, we can look at a t-distribution table, such as in step 8 here, and determine if it is significant. So what you need to do is use your degrees of freedom. We have it here within our table. And we have our t-statistic is here. So if our degrees of freedom is 6, go to degrees of freedom 6, so it's right here. Oh, and just as an FYI, I've taken this table out of a book. So use your own textbook in order to find these tables, or you go online, but the tables should be the same. The values should not differ. These tables are universal and should be trusted no matter where you're finding them, because the values are not changing. Anyway, just to go back now, so the degrees of freedom is 6. We have a degree of freedom of 6 over here in the table. We're going to go across, and we're using a two-tailed test. And if with a two-tailed test, it says right here we want a p of less than 0.05. So if you go up to the top here, we're using two-tailed. So here's the one-tailed above. We don't want that. We want the two-tailed. And the two-tailed at 0.05 is right here. So if we go down, so you can see you almost have to go left from the degrees of freedom and then down from 0.05. Here is the value that sits at the critical region. This value is 2.447. And this is suggesting at 6 degrees of freedom, the p-value equals 2.447. Sorry, the p-value of 0.05 equals 2.447. And we know, if we look at our table over here, our t-statistic is significant because it is 2.69. It surpasses 2.447, not by much, but it does. So therefore, it is within the critical region, and we could assume it is significant. And if it is significant, we can now write a statement that actually says that Bill's walking data does significantly differ from the walking data at the average college campus. So just to recap, were the results significant? Yes, they were. Can we reject the null hypothesis? Yes, we can, because the mean of Bill's data does not equal the population mean of the college student walking data. And then we provide a scientific notation. So right here, this is our statement. Based on the results from our one sample t-test, we can reject the null hypothesis as Bill is walking significantly more, 9.07, than the average college student, which is 7.05, at his college campus. And here's the scientific notation. You begin with t, in brackets is our degrees of freedom, which is 6. T equals 2.69, and it is less than 0.05. So if I was to quickly go back though and look at this table again, let's say we were using a one-tailed test, for example, so not two-tailed, but actually one-tailed, we would look at this top category here. So we would still use our degrees of freedom equals 6, but we would use this top category at 0.05. And you could see here, if you're using a one-tailed test, the requirements to pass or to fall within the critical region are actually a little bit more lenient, because here we just have to have a value that's past 1.94 in order to find a significant result. So that's just really how you use the one-tailed versus two-tailed method. But yeah, so we have our written statement. So yeah, that's how you manually calculate a one sample t-test by hand. In the next video, I'll show you how to calculate the confidence intervals, the effect size, and the percentage variance for the one sample t-test. I'll be providing the same example, but in this case, just providing those additional information you might want to provide, or at least the question might ask for it.